For the first question, we're asked to pick the strongest acid from the following reagents. So looking at pK values for each of these, if we have a hydrogen attached to a carbon with two carbonyl carbons of ketone functional groups right next to it, we're looking at a pK of about 8.9. If we have a hydrogen on a carbon with a carbonyl of a ketone functional group right next to it, we have a pK of about 20. And if we again have hydrogen on a carbon with a carbonyl carbon, but we also have an electron withdrawing group somewhere else in the compound, which we do in this case, it's going to be just less than 20. So we'll estimate this to be around 18 or so. And here we have a hydrogen attached to the carbonyl of two ketones and an ester. If it was just an ester, that pK is going to be slightly higher than just two ketones, but here we have three different electron withdrawing groups. If it was an aldehyde and a ketone, that's 5.9. I'm going to guess this is just less than 5.9, so let's say around 5 with 3 of those. And here we have a hydrogen with sp3 carbon, so that one's going to be a pK of about 60. So for those reasons discussed, that is definitely going to be our strongest acid. That's the most acidic proton. For the next question, select the compounds that are keto, enol, Tautomeric pairs. So in this case, our tautomers, our enol is here and our ketone is here. In all the rest, we have enolate ions. So we have enolate ions or anions. Those are not our ketones or enols, so this one is the right answer for that reason. For the next reaction, draw the mechanism for the following reaction. So here on our carbonyl carbon, we have an alpha carbon. It looks like that alpha carbon was deprotonated. So we need to show our base deprotonating that proton to put our electrons on that carbon, which gets us to this intermediate. Now we have a nucleophilic carbon, which can attack our electrophilic carbonyl carbon and push those electrons up to there to get us to our intermediate, which I'm going to draw it as similar as possible to this, just so we're on the same page for what's happening here. So for this reaction, two different things happened. We converted our oxygen with a negative charge, we protonated it, and we also deprotonated this. So I need to ignore those two things, but just look at the overall structure of this compound. So what we attacked is what will form an alcohol functional group. So what we attacked is that carbon right there. So I'm going to go ahead and draw that as it is now, which now we have an oxygen with a negative charge on it, and that's connected to a carbon, which is connected to two more carbons. What attacked that is this carbon right here, so that bond right there is the bond that formed between these electrons or the carbon which had these electrons and this carbon, or carbonyl carbon. That aldehyde functional group is still attached, so we still have our aldehyde functional group attached to that carbon, which is our nucleophile, and we also have a methyl group. So that methyl group is also right there. So that's the intermediate after this reaction, and I just drew it in a structure as similar as possible to this. All right, now for the next step of this, the byproduct of this reaction was water. So we have our OH attached to a hydrogen, which is relatively acidic enough at least to deprotonate our alkoxide anion to get us to our alcohol functional group. And that is still there, and we still have our aldehyde functional group. And now we have a relatively acidic proton here, so that can be attacked by our hydroxide anion byproduct to get us to this intermediate. Once we have this intermediate, now we can form our alkene via our E1Cb reaction, which once we deprotonate, we can use these electrons to form our alkene and kick off our alcohol functional group to form our conjugated enone. For the next question, pick the compound most likely to form an alkene. So if that alkene can be conjugated with a carbonyl carbon, it's more likely, and if it can be conjugated additionally with an aromatic ring, it is also very likely. So specifically for things that have the carbonyl carbon, it looks like everything on this side does. So these are going to be the ones that are most likely to form the alkene. And then it has to draw the conjugated product. So here we have a carbonyl carbon. On the beta carbon for each of these, we have our alcohol functional group. Our alkene is going to be here, here, and here. So these will not form our conjugated alkene. These will. And then for our conjugated alkene that forms, we have our alkene, which is going to form there. So my alcohol functional group is going to leave. That's where I'm going to form my alkene. On the next one, we have an aromatic ring, which is attached to the carbon, which used to be our alcohol functional group. We formed our alkene there to kick that alcohol functional group off, and we have an aldehyde functional group. And then for the last one, we again have an aromatic ring. We have an alcohol functional group, which is no longer there. We basically kick that off to form our alkene, and we have our ketone functional group there. For the next, draw the product of the following reactions. So for these two, I'm going to just draw the products, then we'll actually look at the mechanism below. So here we have the same structure. So we've got our two ketone functional groups. That is the carbon that was deprotonated. That attacked the carbon, which had the oxygen on it, which would be an alcohol functional group. We'll eventually remove that to form our alkene. It was tough for me to do that because it's a somewhat unstable alkene, but it's possible. And then for this one, the product of this reaction, I'm going to actually show the mechanism within this. So we'll forget about that hydrogen. I drew it right there. So for this reaction, we're actually going to form an enol, and then we're going to convert that back to our ketone. So I'm going to deprotonate that with that, form that double bond, which is going to form my CO2, and then break that bond, which kicks off our CO2 leaving group to form our intermediate, which is this compound here. We have now our alcohol functional group that formed, and we formed an alkene. So that's our enol. And then for our enol now, we can convert this using a base there and an acid there to take that, form our double bond, so reform our ketone and use our alkene to take that acidic proton. And from that mechanism, we're deprotonating this, forming our ketone, so that'll give us our aromatic ring, our ketone functional group, and now we have our methyl group. So we converted our enol, our alkene connected to an alcohol, to a ketone functional group. Now let's go back and look at the mechanism above. So I'm going to make another page here. So for that mechanism, we had our cyclohexanedione ring, and we had a proton right there, and we had a base, AOH, and we had formaldehyde, 2 hydrogens. So in the first step of that reaction, we would deprotonate that, putting the negative charge on that carbon there. So cyclohexane, double bond there, negative charge there. Now we've got a nucleophile, so we can attack that carbonyl carbon there and put those electrons there. And now we have oxygen with a negative charge. We still have everything else on our 6-membered ring. Once we attack that, the book talks about using acidic or basic conditions to show the mechanism to form our conjugated alkene. Since I have H3O+, there's certainly nothing wrong with showing that, but the book never shows a mechanism for it happening under acidic conditions. So I think it'd be best if I just went through and did it under basic conditions one more time just to get you more comfortable with the mechanism. And again, you don't need to know the mechanism if it's under acidic conditions, but we would likely form the enone product regardless of the situation. Again, I'm just going to draw the mechanism under basic conditions because that's what you need to know. Alright, so we're going to form the alcohol functional group. So we have our 6-membered ring here, and we have our carbon double and oxygen there and there. And we now have an alcohol functional group. Now we're under basic conditions again. So we have our OH minus. We have an acidic proton right here. We can deprotonate this to get us to our next intermediate. So still 2 ketone functional groups. Now we have our OH group there still, and a negative charge on our alpha carbon of our ketone functional groups. Now once we have that negative charge, we can move these electrons from the carbon to the bond and kick off our leaving group. So that gets us to our final product, which I had drawn above, but again showing it from the mechanism looks like that. So there is our alkene conjugated with our carbonyl carbons.